Tangents, in this case, well, tangents are related to finding derivatives. However, finding derivatives of functions in the polar system is not as straightforward as finding, a regular derivative. You take the derivative of y equals x squared, well, that's y prime equals to x. Well, in this case, we're working on functions. For example, r equals 3 cosine theta. Well, we would expect that the derivative would be r prime to be negative 3 sine theta. As easy as that, right? Well, unfortunately, that's not the case for functions in the polar system. That's because functions in the polar system, yes, well, we have an independent variable theta and a dependent variable r, which is the radius and the angle and the radius respectively. However, in this situation, all we're doing is finding the rate of change of the radius with respect to the angle. However, the way these functions are defined, this radius and theta thing are defined in terms of x and y, and that x and y, it's going to be this kind of this polar equations here that hold on, these two equations where x equals r cosine theta and y is r equals to sine theta. All right. However, yes, in this case, I know in this case you might be thinking, well, but that's just a number, that's just a coefficient negative 3. However, what happens when you have for example, the graph of a flower like this, Notice how the radius changes at every single point. The radius is not the same anymore as it is, for example, for the circle. The radius is always the same, and that's the only situation in which the radius is the same. So, but not all functions in the polar system behave the same way. So for this reason, we're actually taking this r as a function that varies with respect to theta. So if we take the derivative of this, actually these are two functions, two variable functions, and to differentiate that, we would need the product rule in this case. So that is, I'm going to take x prime, that's going to be f prime g, which is cosine, plus g prime, which is actually negative sine rather, times f. And for the y equation, y prime equals f prime, which is also f prime, g sine, plus g prime, which is cosine, times f of theta. All right? And well, the derivative in this case, well, will be the exact same idea as finding the derivative of a function in parametric form. That is, the derivative of the y equation divided by the derivative of the x equation. In this case, notice we differentiated that equation with respect to the angle, with respect to theta. Well, this f prime theta, it's really the same as saying dr d theta. And in this case, notice how the derivative of the x equation is really dr d theta cosine. That's the same as saying f prime cosine minus r sine minus f of theta, which is the same as the r function. So as you can tell, it's not that simple. Taking the derivative of a function is defined in polar form. It's not as easy as finding dr d theta. In fact, we're finding dy dx, and in this case, we're relying on this polar functions in terms of a parametric function. So, and in this case, it's two parameters, r and theta. But actually, we write the radius parameter in terms of the angle, so we can rely on only one single parameter. Relying on more than one parameter, that's going to be calculus 3 when we look at at functions that depend on one more than one variable, but that's something else. Yes.
On the y derivative, was that meant to be x or theta?
Which one? Oh, yes, this one right here. Yep, this one has to be theta. Thank you. So let's go ahead and do one example. For the cardioid, r equals to 1 plus sine theta, find the slope of the tangent line when theta equals to pi over 3. Well, we have a picture here, so we can, the picture with the information, with important points, you know, some slopes, some points, and, well, you'll see. So essentially we will verify some of these results. So they're asking us to find the slope of the tangent line when theta equals to pi over 3. So number one, we need to find the derivative. Let me write down the derivative of 1 plus sine. So this is f of theta, essentially 1 plus sine theta. And taking the derivative, it's going to be cosine theta. So using the equations that so dy dx, it's going to be, okay, let me write the whole formula in this case. So that's dr d theta sine theta minus, or rather plus, r cosine theta divided by dr, it's dr d theta cosine minus r sine theta. So all we're going to do here is substitute, number one, the derivative right here, which is going to be over here and over there, and for little r, we will replace it with the original function, that is this r right here, which is essentially the same as f of theta. You know, just like when we say y equals to f of x, in the polar world we say r equals to f of theta, right? So let's go ahead and just simplify this. Rather substitute where it corresponds. So dr d theta, that's cosine theta times sine, plus r, which is the quantity highlighted in green, 1 plus sine cosine theta. And then the whole thing divided by dr d theta, which is the quantity in pink. That's cosine theta, looks like a minus, times itself cosine theta, minus r, which is the original function, 1 plus sine, times sine in this case. All right? So let's simplify this. Yes, these ones, okay, when it comes to finding slopes in polar form, these ones take a while, so we're going to be working for a good minute on one single problem. So let's distribute. Let's distribute, multiply by 1, multiply by sine, multiply by 1, multiply by sine. So that's going to be cosine or sine cosine plus cosine plus sine cosine divided by cosine squared and plus or minus 1 and minus sine actually, and minus sine squared theta. Let's see if we have anything to simplify. Well, so yes, so let's combine this sine theta cosine theta. Well, we have two of them, plus cosine theta. And in the denominator, this is what I would like to do. Because in this case, we're going to use both the numerator and the denominator to set them equal to 0 to find both horizontal tangents and vertical tangents. That would involve to solve equations in this case. And well, when it comes to solving trigonometric equations, you might want to leave all these equations, especially that equations in this form, in quadratic form, in terms of one single variable. So what I'm going to do here is leave the denominator in terms of all signs. All right? Well, So here is the thing. Well, so I'm going to replace. What am I going to do here? No, I'm not going to do that. I'm going to, yes, okay. So cosine squared, this cosine squared, let me highlight it. This cosine squared, I'm going to write it in terms of all sines in this case. Well, so cosine squared, we know from the Pythagorean identity that sine squared plus cosine squared equals to 1. That means cosine squared equals to 1 minus sine squared theta. And I'm going to highlight it with the same color just so you can see where is this coming from again. All right? And that's minus sine squared. All right. And then from here, let's just combine like terms. So that's going to be 2 sine theta cosine theta in the numerator plus cosine. And in the denominator, that's negative sine squared, or rather negative 2 sine squared theta minus sine theta plus 1. All right? I'm going to leave it like this for now, but of course when we solve the equation, we will, well actually I will factor this, this polynomial. Well, I'm going to factor this as a polynomial in the denominator. And okay, so that's going to be 2 sine theta cosine theta plus cosine. And I'm going to factor this as 1 plus sine times 1 minus 2 sine theta. Well, how to go from here to here? Well, essentially turn it into a polynomial and factor the polynomial, well, in terms of a trigonometric function, all right? Well, so that's our derivative factored out almost all the way. How about the numerator? Actually, I can factor out a cosine. And that's a 2 sine plus 1. Yeah, it would have been great to have something like this in the denominator, but in this case, well, we don't have anything. So, well, it's going to look like this. So this is dy dx. All right, now they're asking us to evaluate dy dx when theta equals to pi over 3. All right, so that's part A of the problem. Evaluate when theta equals to pi over 3, and well, we should get this ordered pair, and when we evaluate the slope at pi over 3, we should get a -1. So let's see if that's the case. All right, so let's see. So dy dx evaluated at theta equals pi over 3. Notice the notation. It's very similar to what we did back in parametric equation. We evaluated at dy dx, but in this case at a t equals to 5, t equals to 2. Well, in this case we're doing something similar, but at an angle this time. So let's just plug in pi over 3 where it corresponds for theta. So that's cosine pi over 3, 2 sine pi over 3 plus 1 divided by 1 plus sine pi over 3, 1 minus 2 sine pi over 3. And well, how about we just simplify? So cosine pi over 3, that's 1/2. 2 times sine pi over 3, which is root of 3, over 2. Actually, we're going to work with the values of the trigonometric functions in exact form. Plus 1 over 1 plus sine 1 plus sine of pi over 3, and sine pi over 3, that's again root of 3 over 2, and 1 minus 2 times sine pi over 3, that's 2 root of 3. And well, so let's simplify this madness right here. So because we want an exact answer in this case, so these 2's right here, it's kind of frozen here. Okay, these 2's cancel, and these other 2's cancel. Well, I don't know what happened here. And so these two cancel, and that's going to leave us with, for now, okay, let me leave this as, okay, these two in the denominator of the numerator. I'm going to send it to the denominator, multiplying these two factors, 1 plus root of 3 over 2 times 1 minus root of 3. In the denominator, it's the denominator of root of 3 plus 1. And we're almost there as far as simplifying this, this expression. So I'm going to distribute these two over here in the inside of the parentheses, multiply by 1, multiply by root of 3 over 2. And that's going to take us to the following. So in the numerator, we're going to be left with root of 3 plus 1. 2 times 1 is 2. 2 times root of 3 over 2. Well, the 2's cancel. That's just plus root of 3. And that's times 1 minus root of 3. Well, so to simplify this, well, number one, we wish we had a plus over here. This way we can simplify this, but well, we already know that the answer for this should be -1. So what we're going to do here is to FOIL. So distributive property, FOIL. That's root of 3 over root of 3 plus 1 over 2 times 1, that's a 2, minus 2 root of 3 plus root of 3, and well, minus root of 3 times itself. Essentially the radical cancels out, leaving us with a 3. And let's simplify this. Well, number one, in the numerator, root of 3 plus 1 over 2 minus 3, that's a -1, and -2 root of 3 plus 1 root of 3, that's a negative root of 3. Well, notice in the denominator we can factor out a negative sign. If we factor the negative, that's 1 plus root of 3, which is essentially that same quantity in the denominator, leaving us with -1, which is the slope, which actually checks the result that we were expected to obtain from the picture here, isn't it? Here's our -1. All right. Now, they're asking us something else. For part B, they're asking us to find the point on the cardioid where the tangent line is horizontal or vertical. So they're essentially asking us to verify the following points. So vertical tangencies, and horizontal tangencies. Those three. Oh, there's another vertical tangency here. So we'll figure out all of them. All right. So how are we going to do that? Well, so we have a derivative right here. So in order, just the same way we did it in parametric equations, for horizontal tangencies, set the numerator of the derivative equal to 0. And set the denominator equal to 0 for horizontal, and this for vertical. All right. So let's go ahead and do that on the next page. So, well, you can do that on the back side of the page or another page. And so let's see. Horizontal tangencies. So we're going to set the numerator of the derivative, or rather the denominator, not the numerator. Oh wait, no, it's the numerator. That's cosine theta times 1 plus 2 sine theta equals to 0. Well, in this case, we already have an equation in factor form. That is, we can set cosine theta equals to 0 and 1 plus 2 sine equals to 0. Okay? So we have to solve a couple of equations. Well, recall that this trigonometric, when we solve this kind of trigonometric equations, we get pretty much infinitely many solutions due to the property that the trigonometric functions are 2 pi periodic. So you can, so if you get one solution, the first solution, which we usually call the principal solution, you can always add 2 pi to land on the and you will land on the same point back again and add 4 pi, 2 pi, and another multiple of 2 pi. But in this case, since we only want for the solutions when the cardioid is only traversed once, so we're just going to look with we're going to look for the what's it called, for the principal values. And in this case, well, we're looking for the angles whose cosine equals to 0, and the only one is theta equals to pi over 2. All right, it's pi over 2, it's one of them. And over here we need to solve the equation. That's 2 sine theta equals to -1 and sine theta equals to -1. So in this case, this equation is true for 2 angles. Number 1 for 7 pi over 6 and 11 pi over 6. This is just values from the unit circle. All you need to go look for the unit circle and look for the order pairs for which you will see a sign, that is the y value equals to -1/2. All right. And for vertical tangencies, we would need to set in this case the denominator 1 plus sine theta cosine theta. Wait a minute, no, it's 1 minus 2 sine theta equals to 0. So solve 2 equations. In this case, sine theta equals to -1, and in this case, sine theta equals to 1/2. So the sine function is equal to -1. That's only whenever theta equals 3 pi over 2. And sine theta is positive 1/2 whenever theta equals to, in this case, the other 2 angles, 5 pi over 6 and pi over 6. All right, and we can verify these results with the picture that we have in the previous page. So let's look at the horizontal tangencies. So okay, let me go back to the picture. For horizontal tangencies, here we have our pi over 2, this pi over 2 here, the 7 pi over 6, and the 11 pi over 6. And for vertical tangencies, here we can see the 3 pi over 2, 5 pi over 6, and pi over 6. So that is 5 pi over 6, pi over 6, and 3 pi over 2. So everything is verified using setting the equations equal to 0, and this pretty much covers finding slopes, and well, in this case we go a little beyond to find horizontal tangencies and vertical tangencies. Yes?
I saw from the shape that 3 pi over 2 was a vertical.
Uh-huh.
How come from the horizontal it wasn't a cosine theta? Like why?
This is a little weird. Yes, I noticed that too, because, well, in this case, we should have the other solution to this equation is also 3 pi over 2, right? And well, you can verify this in many different ways. I mean, from the unit circle or from the graph. You know, this is one period of the cosine function, and cosine is 0 here and 0 there, and that was what I was going to comment next. So when it comes to work, guys, so when it comes to working in the polar world, we will get a lot of weird results. It's not like in X, Y, we get like in some cases we get extraneous solutions. In other cases, we get pretty much correct results. So in this case, well, yes, clearly, we have a solution at 3 pi over 2. However, notice in this case it looks like a cusp. And at the cusp, well, coming from the left and coming from the right, that gives rise to a vertical tangency in this case, all right? Not a horizontal tangency, because check this out. And you might remember this from calculus 1. So what happens if you do a horizontal tangent at a cusp? Actually, the derivative is not defined when we have cusps, right? However, in this case, coming from the left or from the right, well, in fact, the slope is undefined at the cusp. And well, how does the tangent line look with a slope that it's undefined? Isn't that a vertical one? So in this case, those are going to be a little weird. So in this case, when working with this kind of function, we will need a combination of algebraic techniques, but also geometric techniques. That is to look at the graphs and see what's going on. All right. So yeah, so those are the only potential pitfalls. So in this case, well, let me go back and cross this out as well on the graph, because I mean, algebraically you're right. This is correct algebraically, but geometrically we're seeing a cusp where we have an undefined slope, which technically belongs to the other side of the solution, right? So yeah. Okay, let's go back a little bit to finding areas, and oh my God, this one is going to take forever to go. Hopefully, well, we'll get the chance to at least solve or set up the integral, and set up the integral, and maybe just go a few steps of it. All right. And so that's why, for those of you who have the PDF, I left another whole blank page so you can keep writing the whole thing, all right? All right. Find the area of the region that lies inside the circle R equals 3 sine theta, and outside the cardioid 1 plus sine theta. So that cardioid, it's this one right here that I will highlight it with yellow so you can see it better. So it's outside the cardioid, but actually inside this circle. Okay, that is the shaded region in blue. Well, again, they're being really nice and giving us the limits of integration in this case. However, some weirdness is going to occur in this case. Well, in this case, notice we're finding areas between curves, not an area under a curve. So for this guy right here, well, notice we can use the top minus bottom like we did back at the beginning of the semester when we did areas between curves. However, in the polar world, we don't call this top minus bottom. I mean, we're seeing the top minus bottom because of the configuration of the shape that we want, the setting of what we want to find. But technically, we should call this outer and inner, because we're talking about the radii of these two regions in this case. So in this case we have an outermost radius and an innermost radius. Well, so area, let me define this area as A equals top minus bottom, which is really outer minus inner. All right, outer minus inner. Well, so finding the area equals pi over 2, or I mean 1/2, not pi over 2, area alpha plus beta, and that's going to be, okay, that's r squared. I'm going to call it outer, subscript outer minus r squared inner, quantity squared. Oh wait, no, that doesn't get squared anyway. Okay, d theta. So just like we have a top minus bottom, well, in this case they get squared. So this will be 1/2 the integral. Okay, let me set it from pi over 6 to 5 pi over 6 for now. And well, so this is what's going to happen. So that's the outer function, which is 3 sine theta quantity squared minus 1 plus sine theta quantity squared d theta. And well, in this case, so let's simplify this by writing area equals to, okay, 1/2 from pi over 6. I'm going to simplify the integrand for now. And that's 9 sine squared theta. Squared is binomial, minus 1 minus 2 sine theta. I'm also distributing the negative as I square the binomial, and also minus sine squared theta d theta. And well, the most convenient thing to do here is to combine like terms. So we have a 9 sine squared minus sine squared. That's going to give us 1/2 integral from pi over 6 to 5 pi over 6. And well, that's going to be 8 sine squared theta minus 2 sine theta and minus 1. All right. And d theta, of course. Don't forget the d theta. So what are we going to do? What are we going to do from here? Well, let's just integrate this. However, well, we will need some trigonometric identities and combine a lot of like terms. And in this case, notice the region of integration. Notice how in this case we can write this integral as the integral from, well, 8 sine squared theta minus 2 sine theta minus 1 d theta. And in this case, I'm going to go from 0 to 5 pi over 6. What did I do here? Hold on. No, I think I did something different here. No, I'm going to do not from 0. I'm going to do it from, yes, still pi over 6. The lower limit is pi over 6. Yeah, not 0. But in this case, the upper limit will be pi over 2, which is essentially this limit over here. That is, it's going to be this area right here, and I'm going to multiply this area by 2. I know, I mean, how is this going to make it? How is it going to make a change? It's actually going to make it easier, because in this case we will be integrating between sines and cosines functions, and evaluating sines and cosines at pi over 2 is going to give, they're going to output numbers, zeros or ones. All right, and in this case, well, so we can simplify a lot of work as opposed to evaluating at pi over 6 or in 5 pi over 6, which will get maybe 1/2 roots of 3 over 2, weird numbers, right? So that, taking advantage of the symmetry, indeed makes the problem a lot easier. Well, cancel this. To simplify the integral to simply the integral from pi over 6 to pi over 2 of 8 sine squared theta minus 2 sine theta minus 1 d theta. Okay? And well, we would have to integrate these 3 terms. And okay, for whatever reason my computer froze. All right, got it. No, it's not going. It's freezing. I don't know why. So let's integrate. Okay, 8 times the integral from negative pi over 6. From pi over 6 to 5 pi over 6 of sine squared theta minus 2 times d theta minus 2 times the integral from pi over 6 to 5 pi over 6 of sine theta d theta. And okay, let me make some room over here. What happened? Come on. Thank you. All right. Oh my God, it didn't save well. So I'll have to write the whole thing again, at least these last couple of steps. So that simplifies to the integral from pi over 6 to 5 pi over 6, and that's okay, 8 sine squared theta minus 2 sine theta minus 1 d theta. And then from here, that's the integral. Okay, we're going to get 3 integrals. That's 8 times the integral from pi over 6 to, oh, come on, to 5 pi over 6 sine squared theta d theta minus 2 times the integral of sine theta d theta. And gonna make some room again, make it a little smaller, and plus, or no, minus the integral of d theta and pi over 6 to 5 pi over 6. Pi over 6, 5 pi over 6. Wait, no, this is supposed to be pi over 2, right? Yep, pi over 2. Because we already used the symmetry of it. Yeah, sorry about that. All right, so, well, the second and the third integral right here, we're pretty much ready to integrate this. However, the first integral right here, we cannot integrate it just directly because we have a sine squared. We could use a u substitution if we had a factor multiplying with the d theta that stands to the du part, which is the derivative of sine, which would be cosine, but we don't have it. However, in this situation, we would have to use trigonometric identities. That is the power reduction formula that we have been using since last time, so we can, and that's going to create a couple more terms. All right. However,